Okay, so I hope that we can start from where we discussed in the last week. So in the last week, we have discussed about basically we discussed about random processes. So we have discussed about how we define random processes and how we can mathematically represent the outputs of a certain random process. So first of all, would like to take a certain random experiment, right? And that random experiment can have multiple outcomes. So these outcomes, all of these outcomes can each have a sequence of outputs, um, that that we can show varying against time or some kind of a spatial index. So so basically we call this as sample index. So in a random process, when we compare with the other random variables and joint random variables, random variables and multiple random variables, random processes, the outcomes will be a set of data or a sequence of data that we collect for multiple samples. So if we take the example that we discussed last time, we will consider that same example, and then we will consider other examples as well. So let's say we have a call that we receive from a certain like a base station tower. We receive a certain call. So if we consider receiving a call and receiving a certain call as one outcome of a random experiment where we are going to measure the strength of the signal strength of the call. So in this random experiment, what we are going to do is we are going to measure the signal strengths that we receive under different calls. So for first call, we will be obtaining the signal strengths that we receive over a sequence of time instance. So the sequence that we obtain here will be a certain a deterministic sequence. So this sequence will be deterministic. That means that there will be specific values for the signal strengths at each time. So it's T1, T2, T3. Likewise, we have. Oh, sorry. So I have not shared the screen, I think. Sorry about that. I thought I had shared it earlier. So I was talking about the random processes example. So in the last class, we discussed about this example. So we took a random experiment, and that random experiment is finding out the signal strengths that we receive over different calls, right? So if we receive if we consider multiple calls, call 1 up to call n, we can plot the signal strength that we receive for each call. So if we, I will actually draw this as a continuous signal. So we will be receiving a continuous signal from the base station or from a certain transmitter. We will receive a continuous signal where the amplitude of that signal will vary in a, I mean, sorry, if we are taking the amplitude, it will be positive value. So I will draw a positive amplitude and a signal with a positive amplitude, and the signal strength will vary in a random manner. So if we consider the x-axis will represent the time index, and we can measure the amplitude of the signal at each time. Could be time 1 second, could be time 5 seconds. So for specific time cases, we can measure the amplitude of the signal. So basically the amplitude we will represent as x, and the value of amplitude at t equals 1 second, we will just denote this as x. We will amplitude, we will denote the signal strength as just amplitude, and time will be the x-axis value. So if we consider the second instance where we have another call, the call number 2 will have different variations in the signal strength, which is very different from the first call, right? It can be a different value that we receive at each time instance when we can compare with the first signal that we receive. So some kind of a random signal will be received. So it would also be against the time. So likewise, we will be able to plot multiple sequences of outputs for different calls. So if we take third one, we will be having another sequence here. We will be having another random signal as the signal strength. So if somebody wants to, analyze this system, they can analyze it under the time domain, or else they can also study it across all the different calls. So, in this probability and in this analysis, we call different definitions, or we have different terms that we use to define the parameters across all the different calls, right? I mean, here we are considering calls as the different realizations that we obtain, right? So we will first try to understand the different terms that are used to define a random process, right? And apart from that, so before learning about those parameters, we also want to know that these signals that we receive can either be discrete or continuous. So based on the signal that we receive here, if it is continuous, it's going to be a continuous random process, right? If all the signals that we are receiving, I mean, if the random experiment is producing continuous signals as the outputs under each outcome, then it is a continuous random process. So the random processes can be of two types. The random process can be of two types: continuous random process and a discrete random process. Right? A discrete random process. So in this instance, what type of a random process have I considered? What is the continuous process that I have considered in this instance?
Continuous.
Yes. So continuous random process. So why do we say like that?
So that call is continuously occurring.
Yeah, the
It is varying with the time.
I mean, the signal strength values are received at each continuous time instance, right? There's no discrete, I mean, time instances that we can consider for this case, because we will be receiving a certain signal strength for each time instance between the time range that we are considering, right? Is it? I think it's clear, right? So normally when we are receiving a certain call during a certain time duration, we will be receiving the signal strength continuously. So there will be a value for the output at each at each of the time instances between that time duration. We are receiving a call, we will be having signal strength during the entire duration. Right? We don't have like intermediate locations, intermediate points where we don't have any output. We will always have either, I mean, some kind of a value for the signal strength, right? So I mean, there could be some places where we lose the connection, but even then it would be having a certain value which is I mean, which is a considerable value that we can say that is a above, which is above a certain, like maybe minimum threshold value, um, that that is, I mean, that is there. So anyway, like signal strength we can receive for that certain time duration, then using for all the time instances during that time duration, since we will be having a signal strength, and because of that we will be having a continuous output for that call. So if we consider discrete random processes, discrete random processes means like the output of each of the outputs, and each of the so the outputs of a certain random process can be discrete, if the outputs of that random process are occurring in a discrete manner. So if we take the coin flipping case, if we are flipping a coin n number of times, coin flipping of n number of times, then we are considering the output for each of the n number of times. So each of the n times we are getting outputs for each n for each of the instance. So in that case, we have a specific output for each of the instance of flipping the coin. So if we are flipping it 3 times, then we are getting 3 outputs, and that 3 output will be the output. I mean, for the I mean that 3 out 3 sorry, if there are 3, if you are coin flipping for 3 times, then you are getting for each time 1, 2, 3. For each time you are getting either head, tail, and maybe head. Likewise, you get some output for each instance of flipping. So those kind of outputs are discrete, because for each flipping you get a certain output, but in between two flippings you don't have intermediate values. So in this other instance of continuous random processes, we have a certain outcome or output value for each of the time instances that are there between two limits. So anyway, so there are basically those two types of random processes, discrete and continuous random processes. So we'll be actually looking at, I think, mainly about continuous random processes. And we will be defining the definitions for the continuous random processes. So as with all the other, cases, when we discussed about the random variables, and when we discussed about the random multiple random variables case, and multiple random variable case, we tried to define how the statistics of those variables are defined. So one statistic that we are using is the PDF, and so we have to define the PDF for the random processes as well. Apart from that, we also define the other parameters, such as the expectation operation, which gives the mean value of the variable. We are considering the variable. And so for the random process, we need to find the expectation of the random process. So then we have to find the variance of the random process. So by expectation, what I meant is the mean value or the average value of the random process. And apart from that, we can also find other parameters related to the random process, such as correlation, covariance, and likewise, we have statistics that we will be able to discuss. So I think we will discuss about the probability density function about the random processes. So do you have any questions so far? Before going for the probability density function, I think, like as I said before, I will be able to I will be basically defining the different terms that are used to define the random process. So a random process is I will use this diagram. So I mentioned to you in the last class that when we consider multiple realizations, so um, so the first definition is that the output of one outcome is that now this is one outcome of the random process. So for each outcome, we can obtain a sequence of data. So this sequence is one sequence that you obtain is known as a realization. This is known as a realization. This is also called sample function. Sample function. So sample function means that for one specific outcome, what is the function that that is showing the variation of the specific parameter we are considering against the time or against a certain sample index. So each of these are realizations. They are known as realizations. So uh, when we consider all these realizations, right, we can either like find the parameters related to one realization, or else we can consider all these realizations and we can find the properties of all these parameters under a specific time instance, right? So if we take the x-axis is time in this instance, we can consider specific time instance, such as, for example, let's say we are considering time instance of 1 second. For each of the plots, we are considering time 1 second, and in that instance, we are going to measure the amplitude that we receive, t equals 1 second. Then the amplitude under that instance, we are going to consider, and then we are going to understand, or we are going to study the probability density function in that time instance, right? So for each of these amplitudes that we consider in the plots under t equals 1, we will be able to get different amplitudes, right? We will be able to get different amplitudes. So let's say we are going to measure the amplitude that correspond to 1 second for each of these realizations, right? For each of these realizations, we are going to consider the amplitudes, and we are going to plot the probability density function of those amplitudes, right? So the probability density function, those amplitudes, we are going to plot. So the probability density function we define as the function that varies with the random variable x of 1, right? So the random variable in here we denote as x1, right? So x1, and then inside brackets simple x, and then as the random variable we consider x1. So the probability density function. So for a for modeling the signal strength that we receive over a call, we normally like consider that at each point in time, the amplitudes of the signal varies according to a certain distribution, and it is it is defined in theory, and it is standard. It's the standard theory used to define the variation of amplitude in a telephone call. So this distribution is known as the Rayleigh distribution. So we normally consider this Rayleigh distribution to denote the signal, the probability density function of the signal strength at a certain point in time. So when we try to so the Rayleigh distribution looks like kind of like this. So the Rayleigh distribution can be used to denote the random variables probability density function at each time instance. So for each time instance, this same probability density function is used to model its probability density function. So for each time instance, you can consider the same probability density function. So if so that is one thing, and um, so all the set of all these realizations we call as the ensemble of the random process, right? So ensemble of the random process is something that is very important, right? So we have to know its definition. So we will try to write down the definitions of different names that we are using under these random processes, right? So basically the random process is basically defined as the ensemble. Random process is defined as the ensemble of deterministic sequences or deterministic realizations. Right? So ensemble is actually a collection. It is actually a collection of all the possible deterministic realizations that are possible from this random process. So each individual sequence, right? Sorry, I will describe the ensemble. So ensemble is the set of all possible, the set of all possible sequences. The set of all possible sequences or realizations the set of all possible sequences or realizations we call as ensemble, right? So, so what is realization? So realization is the each individual sequence. Each individual sequence that correspond to a specific outcome. So there could be several outcomes. So for each specific outcome, what is the individual sequence that we receive, and that received sequence is known as the realization. So each of these singular plots are realizations. The set of all these plots we call as the ensemble, right? So ensemble we actually study under certain time instances. So we can study the ensemble by studying each of the time instances separately. So basically, right? So there are so many data points in all these different plots. In order for us to identify some kind of a knowledge or identify some kind of pattern, some kind of information, useful information about those plots, we need to study the plots under specific time instances. So when we are trying to find the ensemble and we are trying to study the ensemble, we are going to specifically consider one specific time instance and then compute the parameters related to that specific time instance, right? So so when we are considering about the ensemble, there is something called the ensemble average, right? So ensemble average, right? So the which means the average of the um, of the parameter xt. So let's say now in here we have considered x1, right? x1. So ensemble average at t equals 1 second we call as ensemble average at t equals 1 second. So ensemble average at t, right? T equals 1 second we denote as x1. So ensemble average is the average of xt at a certain t value, time value. So so the ensemble average we can find using the definition of the probability density function, right? So we know that the xt is following a certain probability distribution or density function like the Rayleigh function. That Rayleigh function is denoted as fx1, then inside bracket x. In here, I will denote that the variable as x1. Variable is now x1. So the probability density function is the Rayleigh function, and it can be used to find the expectation value. So the expectation value of uh, the ensemble we can define using the integration, where we take the variable and multiply with its probability density function, and it is denoted using this. So the expectation of the variable x1 can be denoted using this integration. So this one we can call as the ensemble average. The ensemble average at t equals 1. So likewise, we can compute the ensemble average at each point in the process. Each time instance of the random process, we can consider the ensemble average, right? So if the ensemble average that we compute, ensemble average that we compute does not vary. If the ensemble average does not vary, we call such processes, random processes, as stationary processes. So if the ensemble average is constant, at each point in time, then we call that process a stationary random process. Stationary random process. We will learn about the stationary random processes as well. So basically, we will keep in our mind that once the ensemble average is equal at each point in time, then that process is known as a stationary random process. Apart from that, there are other types of processes which we call as ergodic random process. Ergodic random process. Ergodic random process occurs when the ensemble average is equal to the time average of the realizations. So ensemble average is equal to the time average, right? Time average of time average of any single realization. So if the time average of any single realization is equal to its ensemble average, then that random process is called as ergodic random process. So in that case, we are relating the time, the average over time with the average over the different outcomes of the random process, of the random experiment. So we are relating time axis and the outcomes, and we are relating the averages of the times and the average of the outcomes. So in this instance, basically we can give the behavior of the random process using any single realization over time. So the behavior of a single realization, is representative. The behavior of a single realization is representative of the statistical properties of the entire ensemble. So what I mean is that by looking at one single realization, I can say the statistical properties of the entire realizations. You know, by looking at one realization and its properties over time, I can say something about all the realizations of the random process. So up to this point, is it okay for you? When we talk about the time average, I would like to define that also using some integration mathematical formula. So the time average of a certain sequence, right? Time average of a certain sequence, we can denote using this equation, right? So if you want to find the time average of a sequence, right? So in here, earlier we talked about the time average of a single realization. If you want to find the time average of a single realization, right? We can find that using this integration, right? So time average we can find using this integration where we send the limit of time to infinity, and we take the integration of 1 over t, and from minus t to plus t of the of the sequence which is varying with the time. So in here actually this is the the basically the values of the amplitude over time, right? So the values of x over time and integrated with dt. So I will say that this is xt dt, right? Xt dt. So we are not considering specific time. We are varying the time over minus capital T up to plus capital T. And I'm taking the integration with respect to time axis. This T value is the period of the signal, right? So in random signals, if it is a random signal which varies very frequently, and that the pattern of the signal, I mean the amplitude of the signal does not, I mean, show any pattern. So let's say now this is a random signal that we receive from one of the calls, right? So it could be some kind of a random signal, right? So I will try to make it as random as possible. Can't be like similar in two positions. So if that is varying like this signal, Then in order for me to find the time average, I need to take this integral where I take all the values of the signal, signal amplitudes, and average it over the total number of signal total number of instances that I considered. And that I can do using this integration, which is basically, this integration, which is a normal standard equation that is used to find the time average of any signal, any kind of a signal which varies over time. So this part is used to find the average of any kind of a time series uh, signal. So however, like this is for a periodic signal. If we take this integration only, this part is for periodic xt signals, right? So in order to, I mean we can use this equation to find the average of periodic xt signals. So we can find the average of periodic xt signals using this equation. So in this equation, why did we send, so in order for us to find the time average of this random sequence, the random sequence over time, why did we select t goes to infinity? Why did we select t goes to infinity? So is this random signal periodic signal? Is it varying in periods? Are there like periodic patterns in this signal?
No,
So yeah, so thank you for,
No, random.
yes, it will be very random and the amplitude will be very varying very randomly. And therefore, this is not a periodic signal. So if that is not periodic, then what would be the period of this signal? If you are going to consider a certain period, what is going to be the period of this signal? Right? So for a non-periodic signal like this, we consider mathematically that its period is actually uh, its length is infinite. So the period length is infinite, which means that the time period is going up to infinite time period, which means that this random process is period is it shows its periodic behavior only after an infinite time duration, which is actually something that really is something that we cannot really even show using using figures or any demonstrations. But what it actually means that we can consider any signal which is not showing any pattern, that its period is infinity. If it is infinity, then we can consider that that same behavior will most probably will be repeated in the next infinite time duration. But infinity is something that we cannot end. So so the period of this non-periodic signal is no is considered as infinity. So because of that, we send the time period up to infinity, then do this integration, which we normally do for the periodic signals, to find the average of the signal. So the time average we can find by sending the t value to infinity in in this integration. So by doing that, we can find the time average. So I will now like try to draw in here a small diagram that showcase the definitions that we have talked so far regarding the different parameters or like parameters related to this random process, where we consider each outcome as, let's say, eta or theta. So theta 1 is the outcome 1. So each outcome we denote using theta. So each outcome we denote using theta, and then we can denote another parameter, which is the time parameter. So the time parameter, uh, we call that, actually in general terms we call that a sample index. Reason is this sequence that we obtain for each outcome will not only depend on time all the time. It can be depending on the spatial coordinates, right? Spatial dimensions. So because of that, we are generally referring this x-axis variable as the sample index, over which we are plotting the values of each output we receive under the sample index. So the sample index we denote using, let's say, n, right? So let's say it's n. So we will denote n as the general term used to denote the sample index. So the sample index can be another parameter that we use to define this random process. So we can consider cases where we consider the outcomes, and we consider a case where we consider only one outcome, right? One outcome, or a case where the theta is fixed. And then we consider a case where theta is varying, right? So theta is a variable. So what I mean is that we are considering the values of, if we are considering the values of all these plots along the y-axis direction, if we consider the values of all these plots under y-axis direction, we consider that the theta is varying. Theta is varying. If theta is fixed, then that means that we are considering only a specific outcome. So theta is fixed means we can consider a specific outcome. So it could be one of the outcomes like this. So we are considering a specific outcome. So in that case, theta is fixed. So theta is variable if we are considering the different outcomes we get. Different outcomes we will get once we vary the theta value. So in that case, like what happens is something that we are going to just look at. So So theta can be varied along the y-axis, and theta will be fixed for theta will be fixed for one plot, one realization. So when we consider other variations, we will consider that n is fixed and n is varying. N is a variable. If theta is fixed and n is fixed, right? N is a specific value. Let's say n is 1 second, and theta is fixed. That means we are going to consider only one realization. If it is like that, what is the output that we will be able to obtain? Is it a point in the plot, or is it a random variable, or is it a sequence, or is it a process, as you think? What do we get once we consider the specific realization and a specific time index? What do we get? Is it a point? Or is it a collection of points? Okay, so Matan says is period. No, actually, we get actually a point, right? So if we take a certain specific realization and if we consider specific time instance, then both of those will satisfy one point in that certain specific realization. So in that case, what we will get is a certain specific, like a number, certain number or a certain point in the plot. If we keep the certain realization, we keep the realization fixed, and we are varying the indexes, right? If you are varying the indexes, sample indexes, what do we get? Do we get a point, or do we get a sequence of points? So we get a sequence of points, I think, right? So sequence of points, you get um, a sequence of points, or we can call this a sample sequence, or we actually get the realization. Sample function. Sample function. We can call this also sample sequence. We can also call this as realization. So we obtain a realization once we, if we keep the outcome fixed, and we vary the sample indexes over certain, over a certain range, right? So over a certain range, we are varying the sample index, and then we are considering that for a certain outcome, for a certain theta value. So that is what happens when we keep the theta or outcome fixed and the sample index as a variable. If you are varying the realizations, that means if you are considering all the realizations and we are considering only one time instance, what is the thing that we can observe? What is the I mean, what is the resultant? I mean, resultant. What do you call? What is the resultant thing? If we consider only one time, let's say one time instance, if we take t equals 1 second, if you take all the amplitudes of all the realizations, what do we get? So all these amplitudes that we collect at a certain time instance will behave as a random variable, right? All these amplitudes will have a random value, and they will be having a certain probability of occurring, and there will be set of amplitudes that can occur in this system. And so likewise, it will satisfy all the features of a random variable. That random variable we can study based on its other parameters, such as how its probability density function is defined, and how its other parameters such as mean of that random variable is defined, variance of that random variable is defined. Likewise, we can define different parameters for this random variable. Anyway, what we get at a certain time instance is a set of different amplitudes of the signal which correspond to a certain random variable. So the random variable is something that we will get in this instance, where we consider all the different realizations under a certain time instance. And if we consider all the different realizations and we consider all the time instances at the same time, we will be basically considering the entire random process. So the entire random process is basically this entire thing. So this entire, like all the realizations that we can obtain as outputs of this random experiment, and all the realizations, if we take collectively over all the time instances, we can call this as the random process. So if you have any questions, you can ask. So I would like you to have a 5-minute break. Then we will start it at 10:10. If you have any questions, you can ask at 10:10. Okay.
Hello. Oh, hari may I
Right. I will start the rest of the sections. So this entire thing we call as the random process, right? And the entire thing we call as the random process. Then we can go to the other definitions. Before that, I would like to state that once we are using this random process, the term random process, we can use random process or we can use the stochastic process at the same time. So which means that the words stochastic is equal to the random word, which means that stochastic signals and stochastic processes are equal to random processes. So instead of random, sometimes we will sometimes hear stochastic word. So we know that in, for example, there are algorithms called stochastic gradient descent. Stochastic gradient descent. So this algorithm is working under this random um, under using a uh, random selection process where that algorithm selects some random numbers um, based on the whatever the data points it has, then selects the one, I mean, selects a random point to calculate the like some kind of gradient in that point and so on. So stochastic word is also used interchangeably with the random word. So random processes, stochastic processes, those mean actually the same thing. So I think uh, so before going further, I think we will consider one example to understand the definition of ensemble. So we will consider this example first. So I want you to consider situation where we have like finite number of realizations, right? We have finite number of realizations. Finite number of realizations means there are finite number of output realizations. So 1, 2, 3, 4. Likewise, we can count the number of realizations. So let's consider a random process with finite realizations. So consider. So I'm going to consider this as one example. So consider a random process that is defined consider a random process. I will write it as RP. Random process defined by finite number of finite ensemble, finite sized ensemble that consists of four realizations. So the realizations are basically x, t, comma 1, right? One realization is t comma 1, which is equal to, which is behaving according to the function minus 3u and ut. So unit function. Then xt comma 4, right? So which means that these realization values are behaving against the time, and it corresponds to the certain outcome number 4. Sorry, I will put number 2 first, which is cos pi t plus, sorry, pi t ut. Thirdly, xt comma 3 equals uh, to tut. Fourth one is xt comma 4 equals 2 sine 6 pi t plus 0.2. So we are asked to, the first question is draw the ensemble. Second question is find the sample space at the time equals at time t equals 0.2. So can you try this? If you have any questions, you can ask. We will give you 2 minutes. So shall we try to draw the ensemble? Drawing the ensemble means drawing all the possible realizations. So all the possible realizations are four. I mean, there are only four realizations that are defined for this random process. So this random process has only four realizations as the outputs. So there are only four realizations, and the ensemble means all the realizations. Ensemble means all the realizations that are possible from this process. So all the realizations possible from this process. So there are four realizations. So what we want to do is just draw the all these plots. So the first plot is the plot with -3 ut, which means that it's having -3 value, and it's constant over the time. So it is a function of xt1, and its amplitude is in the negative direction, and its amplitude is constant. And then secondly, we draw this cos function with respect to t, and its function is xt2, and its value is changing based on a cos function, and the frequency of the signal is depending on pi. So you can decide a frequency on your own, and you can basically draw the cos function appropriately using some kind of help from the scaling. Then you can draw a cos function around the time axis. So you can draw a cos function. So it should be more circular and more smooth. So you can define this as the cos function, cos pi t into ut. So ut actually means unit function. So if you're multiplying with ut, it means actually you're actually just considering the value of cosine and then multiplying it with the unit value. Unit function, unit value means 1. Basically you're multiplying each cos value with the 1 with 1. So we have the cosine function as the second realization. Third realization is basically the function 2t ut. So 2t ut is function that we can draw as a slope, and we can denote it like this. So we can denote the function varying with the time, and its amplitude we denote as the amplitude varying with time and corresponding to the third output, and the function looks like this. Lastly, we have another sinusoidal function. So it is basically sine function, which is 6 pi t plus 0.2. So in that case, we have to draw a sine function which has 2 times the amplitude that we had earlier. So basically like this, but it is a sine function. Also, it is a like function which has a certain offset of 0.2. So we have to get the peak of the sine signal. It will be to offset at the beginning, and then we can draw the sinusoidal signal. So basically, we will draw it like this, where the peak of the sinusoidal function has been shifted by about 0.2, and then the rest of the wave form will also be like following that offset, and that sinusoidal function is considered. So we will draw sinusoidal function like this. So I want to actually make it twice the amplitude of this signal, right? But it's going to be a very big wave. So because of that, I'm just going to draw it in a like a manageable size in here for the moment. Right. So since it has higher frequency than earlier one, we are going to draw it with a higher frequency. So it should be sinusoidal signal with a higher frequency than the previous cosine signal, and it will have sinusoidal nature. So basically, this would be one of the waveforms. So I don't want you to like exactly detail each and every point in the signal. You just need to draw the signal using just showing the shape of the signal. So this signal we can denote as the signal xt4. xt4. So basically that would be the answer for the first question, where we draw all the realizations. So these are the all realizations. Second question is that we need to find the sample space. We have to find the sample space at time equals 0.2. So in the time equals 0.2, the sample space we can find by finding the value of these realizations at the time equals 0.2. So for each realization, we can go and we can substitute t equals 0.2. So we can do that by substituting t equals 0.2 for each of these functions. So t equals 0.2 for each of these functions. So we can easily sometimes find the values of t equals 0.2 for the first one. Of course, the t value does not interfere with the amplitude of the signal, right? So although like it's multiplied by ut or the unit function is a function which is constant throughout all the time values. So its value does not change for, uh, for a certain time instance. For t equals 0.2 also, the ut value is 1. This value is 1 for t equals 0.2, and the resultant value from the first realization at the time t equals 0.2 is now x 0.2 comma 1 is -3. Then x 0.2 comma 2 is basically, once we substitute 0.2 inside here, which is cos pi 5 pi, and time is 0.2. 0.2 is we want to just simplify 0.2, it is 1 over 5. So I can substitute 1 over 5 and then ut. So in here, so in the ut also we can substitute t equals point something, we can 0.2 we can write here. Whatever the value of whatever the value of time, u value or ut value will remain as 1. So because of that, the remaining will be cos pi, which is equal to -1. Thirdly, x 0.2 comma 3 is equal to 2. 2 into 0.2 into ut, u of 0.2, which means that this value is 1. So final value will be 0.4. Finally, we have the fourth realization where we can find the value by substituting the 0.2 into the function here. So, right? So if I feel that this is difficult, I can also use the MATLAB interface to find that. So if I want to find the value of the function at 2 sine, I'm going to type it. So 2 sine 6 pi into 0.2, which is the time, plus the 0.2 offset. I'm going to get this value as the output. So this is the output for the output value for that. So I'm going to get that as the output. So basically, I can write that as the output here. So these are the values that I got as the specific values at time equals 0.2. And therefore, those values correspond to the sample space that we can obtain for that specific time instance. So the sample space at time equals 2, sorry, 0.2 is equal inside brackets minus 3 minus 1.4 minus 1.4736. So do you have any questions so far? I mean, these are the answers or solutions we can compute for this question. Do you have any questions?
Madam, can you explain the fourth graph which you followed? I mean, x is equal to T3, the fourth, last one. Yes.
Third one?
Last one, T4.
This one?
Yes.
So this is a sinusoidal signal. You're asking about how you can draw the graph?
Yes.
So basically, it's a sinusoidal signal that now we can have a sinusoidal signal of certain frequency first.
Yes.
So I mean, we can first draw the sinusoidal signal starting from 0, and we can draw the sinusoidal signal with a certain amplitude. So if the amplitude is 2, we can define 2 here, and then you can define the frequency based on the 6 pi frequency that is the frequency of the signal. However, like once we have a certain offset, we have to offset this signal by that specific time value. So that means that if, for example, at time equals 0, we have to see what is the amplitude that is occurring in this signal. So we will substitute t equals 0, which means that at time equals 0, the value of the sine function will be 2 sine 0.2, right? So we will see how it is like. So 2 into sine of 0.2. It's going to be something 0.3973. So we will draw the amplitude at that point to be 0.3, 0.37, that value that we got. Then we can also substitute different time values for this and see, like at time equals 10 or something, you can see how the output varies. And likewise, you can consider those cases. Then you have to draw the sinusoidal based on the amplitude that you get for each of the time values. So based on the frequency, you can define what is the time period of this signal. So the frequency or omega for this signal is 6 pi, right? So omega is 6 pi, so omega is also 2 pi f. So omega is also 2 pi f, and this is equal to 6 pi, and then frequency is equal to 3, right? So in that case, I will get as 3 equals 1 over t. So as for the period, I will get something like 0.33, 1 over 3. And then I will use this as the time period for my calculations here. And like I will compute like what is the amplitude that occurs at the signal when the time period is directly at 1/4 of this time period. So if I want to find the other points, data points, I need to substitute the t values in here and then find the value of the amplitude. So basically in here, actually, I have drawn only the first point, actually, the first point that relates to the 0.3 of that relates to 0.379, that value that we can get. So if the maximum value of the wave, it should be 2, as I understand. So if the amplitude that we get at t equals 0.2 is below the peak value, right? And if the time is also below the time period or below the value that we can get in here as the, let's say, 0.3 divided by 4 should be, I think, a very low value, right? So anyway, I think we can correctly define the value of the point where the peak occurs, and then based on that we can draw this signal, right? We can correctly draw this signal. I think maybe the peak will come maybe like maybe this so I think like this point should be 0.33 divided by 4. So let's say it's 0.33 divided by 4. It's going to be 0.0825. So in this point, sorry, in this peak point, the time equivalent value is, so I will first, I need to delete this one because this x or this point is the origin, so it is equal to the t equals 0 point. This point equals to t equals 0, and then this point equals to t equals 0.2, something like that. At that point you will get a peak value. So likewise, you can consider the values for each of these specific special points. Then you can consider the amplitudes that you get at that points, and then connect them using a sinusoidal wave. Is it okay for you? Okay, thank you so much, Mathan. And that is basically regarding that question. I think that like once you draw the sample diagrams, I think it's very easy for you to find the values of the functions. And you can just substitute the value of the time for each of the realizations, and then you can find the values of values for that specific time instance, and you can collect them all into one, and you can show that that is the that can be considered as the sample space for that specific time instance. So if you want, you can use MATLAB to compute these things. You are doing it as assignment, of course. So MATLAB is a good calculator for you to use when you want to do some calculations. So that is regarding the ensemble and the sample space of a certain ensemble. So we can then move on towards some definitions regarding the random processes. So do you have any questions so far? As I said before, now random processes can be studied using the probability density function of the random variables that occur in the random process under each time instance. So now we said that now each of these random variables, right? Each of these random variables that occur at the time instances, such as, let's say, time instance 1 second, time instance 1 second. At time instance 1 second, we can collect we can collect all these amplitudes, and we can draw a certain probability density function. So that probability density function is defined for this specific random variable. And for this specific random variable, we can define the cumulative density function as well. So this is the probability density function, PDF. We can draw the equivalent CDF of this as well, right? So the CDF function we can draw by integrating this PDF function over the time duration that is considered, or over all the random variables that is considered. So we can draw the PDF of the certain random variable x1, right? CDF of x1 we can denote by taking the integration, and we can consider that the integration will somehow reach 1, right? So CDF function will always finish or end at the value 1, right? The reason being that once all the probabilities that relate to all the different random variables are accumulated, the final accumulation value, the final sum will be equal to 1. So this final value will equal to 1. The CDF value will equal to 1 once all the random variable values are considered. So if we take random variable x1, we can consider CDF value as the value that we get by integrating the PDF function at each random variable. Sorry, I mean by considering the PDF function for a certain random variable. So for a certain random variable, we can define the CDF function of that random variable, right? So for each point in the time in this axis, we can draw a probability density function like this. So what it means is that each point in this time axis is a random variable, right? Each point. Yes, do you have a question? So each point in here, each different point that we can consider in this time axis is a random variable, is a unique random variable. So what I mean is that the random variable at time equals 1 second will be different to the time variable at t equals 5 seconds, right? So the random variable, if I take at t equals 5 seconds, it will be different to the random variable which is at t equals 1 second, right? There are situations where these random variables behaviors are same, right? So in general, we can say that the random variables for each time instance is different. So we can define the probability density functions and the cumulative density functions for each of these random variables, right? So we can denote them mathematically as well. We can denote those CDF PDFs as mathematically as well. So I will denote that mathematically as well for the completion of the theories, right? So I mean, we can define the CDF first, CDF function first, right? Using the CDF, we can derive the PDF. So CDF function for a certain random process with random variables x1, x2, x3 up to xk under the certain under certain time instances n1. Let's say the time instances are denoted using n. Okay, so this is time value. Let's say it is a time value. It can be a time value, or it can be another sample index value. So the CDF function we will consider under this time instances n1, n2, n3 up to nk. So if we consider this CDF function, we'll be considering the CDF of x1, x2, x3 up to xk random variables, and it will be defined as the probability of obtaining the random variable xn1. So the random variable at time equals n1, right? The random variable that we can generate for a certain time instance, right? For a certain time instance, we can generate a random variable, and that one we can denote as xn1. So the random variable we can define for certain time instance. We can so the random variable we define for a certain time instance. So that all these time instances collectively we consider as a random variable, and that random variable value, the value of the random variable should be below a certain, should be below a certain, if it is below a certain x value, let's say x1 value, right? It could be a specific amplitude, right? A specific amplitude. This is xk value. Let's say this is generally some xk value. Denote a specific amplitude value of x at time k. So specific value at time k. At time k, right? So this probability that we are trying to find is the probability of the random variable xn1 being a certain value below this specific x1 value. And then same thing for other random variables, xn2 being a value below x2, xn3 below certain specific value x3. Likewise, up to a point where we go until xk. Until xk, we can go defining this inequality, right? And we can say that the probability of this occurring is the probability of this CDF function, or the CDF function gives us the probability that the random variable values are below certain fixed values x1, x2, x3 up to xk, and that value we can find using this CDF function, which so this CDF function is defined under x1, x2, x3 random variables. So this CDF function is defined under like multiple random variables. So using that multiple random variable based CDF function, we can find the final value of the whatever the CDF function, which relates to the probability of random variable being below certain specific values that we fix. So similarly, we can define the PDF function, right? The CDF function we can denote mathematically as capital Fx, and we can denote this as x1 up to xn, right? So there are multiple random variables in this case we are considering. So if we are considering random process, we are going to be considering x1, x2, x3, likewise up to xn, up to multiple number of x values or random variables values we are considering. And in here, I'm going to put capital F, capital X as the subscript. So as the subscript, capital X. So inside this function, inside this bracket, I have all the random variables that I'm considering. inside my CDF function. So CDF function will give me the total probability of all these random variables being a certain limit, right? Under certain limits. So this function is the CDF function. If you want to find the PDF function, we can find the basically PDF function by taking the derivative of the CDF function. So the PDF function we can denote as the derivative of the CDF function. So in here I have taken up to nth variable, so I'm going to do the same. So until all the variables, until the so we consider all the variables from 1 to n here. So until all the variables are satisfied, we are actually doing the integration or the derivation differentiation. So in here we can denote the PDF function as a differentiation with respect to all the random variables that we consider at a certain time instance. So if you are considering x or n number of random variables, we will be doing a derivation differentiation, right? We will be doing a differentiation up to the nth order, and it will be like this. So x1, x2, x3 up to xn. And then we are going to take the derivation with respect to all the random variables, the delta x1, x2, x3 up to xn. So when we take this derivation, we will be able to get the value of the PDF function at each random variable value. So then, so that is basically the mathematical definitions of these PDF and CDF values, I mean, of the random process. However, these equations are really long and complex, and it doesn't really, I mean, it is kind of like, it looks very complex. So you don't actually have to, keep remembering this, but you can understand how it happens. I mean, you can keep in your mind this definitely, but you can understand the concept behind this, and then I think it will be easier to understand and maybe learn this well. So when we talk about the other parameters that are essential for us to identify the random process, so the main parameter that we will be focusing is the average value, right? Average value. So average value is the uh, the whatever the ex value, right? So we take a random process, the mean value or the average value is obtained by taking the expectation operation on the random uh, process and at a certain time instance, right? So we can actually consider, I mean, I will like to rephrase my definition about the average. So the average we can consider under ensemble average or time average, right? So in here actually we are going to consider the ensemble average and ensemble mean, right? Ensemble average and ensemble mean, sorry, ensemble mean and ensemble variance, right? So these are the main two parameters that we discussed about in our previous classes, when we discussed about the random variables and the multiple random variables case. So in this case, we are going to consider about the ensemble, right? So ensemble, let's go back to this diagram. Ensemble is something uh, that we can, so ensemble is set of all these realizations, right? Ensemble is a set of all realizations. So ensemble average is the case where we consider a specific point in this time axis, and then we consider all the amplitudes in those time axis, and then we take the average of all the values, right? So we take the average of all these values, and then we can find the average random variable, average value of the random variable. So however, we know the PDF function of this amplitude at time equals 1 second. We know the PDF value. We already know this fx value, simple fx value, right? So since if we already know the probability density function, uh, right? Probability density function of, let's say, x1, right? If we know the PDF function already, right? It could be the Rayleigh function, right? It could be the Rayleigh function. So if we know this PDF function already, which shows us the behavior of x1 with respect to its probability density, which is also denoted as fx1 x. So this, once you know this function, it's very easy to find the expectation value. So the expectation value is basically taking the integration of taking the integration of this uh, function, PDF function with the x. So ext, right? Let's say x1 in here, since we are considering x1's average, then its value will be from minus infinity to plus infinity, or for whatever the range we are considering the x variable. And then we are going to take the product between x and fx1 probability density. So this equation will give us the ensemble average at x1. Ensemble average at x1, right? So ensemble average of the random variable x1, let's say. So it is the ensemble average of the random variable that occurs at time equals 1 second. Right? So this random variable occurs at time equals 1 second. So this ensemble average is computed like this. So for a general scenario, we can define that the ensemble average at time t, at a certain time t, is denoted as ext equals minus infinity to plus infinity x into fx and x, right? X of that certain time instance. So to denote the time instance, we will put x comma t, then dt. So dx, we are integrating based to the random variable. So so this is how we can denote the mean value of a ensemble, right? Of a certain ensemble that occurs at a certain time instance. We can consider the instance using this t value. So you can, if you know the probability density function, you can find the mean value. So when you're computing the variance value, right? Variance value you can also consider for a certain time instance. So that right, variance value you define as E, let's say, for a certain time instance T, it's going to be expectation of xt minus mu t. Inside curly brackets, it's going to be squared, right? So because we are taking the variance, right? So this is the definition of variance, right? So variance means like the gap between the mean and the value of the random variable into squared. It gives us the power of the signal as well. I mean, it gives some sort of a sense of like what is the gap between the average and any value of the random variable in the selected random process. So this is how we can define the variance, like, right? So basically ensemble variance we can define like this. So we take the ensemble average in here. So this is the ensemble average, right? Ensemble average is mu t, right? So it is what we define in here. In here we defined as ext is mu t, basically mu t. Yeah. So ext is basically mu t, which is the average of all the amplitude at a certain time instance. And this is the variable that we define at that certain time instance. Apart from that, there are other parameters. So yeah, apart from that, now when we are dealing with different random variables across the time axis, we can draw the mean values that you get along the time axis. So along the time axis, for t equals 1 second, we can obtain a certain mean value and we can plot that. Right? We can plot that as the mean value of that time at that time instance. Right? So if we are going to plot the values of mean at different time intervals, time instances. If we can consider that for 1 second, we can get a certain value. That value we can, we can have a certain specific value. It could be 0.2, 0.3, something like that. And then for another time instance, for 5 seconds, let's say, it's going to be another value. So likewise, for each time instance, we can consider different mean values will occur. Right? So different mean values will occur. We don't know the exact value all the time. So it depends with the specific random process. So these values that we get will be, they will have a certain fixed value. So because of that, this sequence of mean values across the realization, right? Once we are moving across the realization, the mean value of ensembles that we can get will be a sequence like this, and the sequence will be deterministic sequence. So this sequence will be deterministic sequence. And so we drew this for the mean value. Similarly, for the variance value, you can draw another sequence that can display us the variance of the random value at each time instance. 1 second, 2 second, 3 second. Likewise, for each time instance, you can draw the value of the variance. So once you draw the value of the variance, it will take like a pattern similar to a certain sequence, right? So that sequence, it will also be a deterministic sequence. So this deterministic sequence is something that will denote the each of the variance values at each of the time instances. So do you have any questions so far? Another thing I want to mention here is that these values of mean and variance do not depend on the other variable. So these two values, right? These two values are not interdependent, and they are not depending on each other. So these two values are not interdependent. They are unique on their own. Those values are calculated on their own random process. They are not interdependent. Right? So, however, if we want to find the interdependency, right? So there could be some dependency, right? Most of the time, in general, these two values are not interdependent, right? These are not interdependent. So in cases where we want to find the interdependency between two signals, two realizations, right? Or 2 points in the same realization, we can find the value or the statistic value of the statistic called autocorrelation, right? So in the last class, we learned about the correlation, covariance, those statistics. So those statistics are what we are going to discuss about. And this statistic is autocorrelation. So autocorrelation function is defined as the correlation or the dependency between random variables T1 and T2, for example, right? So if there are two random variables, xt1 and xt2, if there are two random variables, xt1, xt2, then if you want to find the autocorrelation or the interdependency between these two random variables, we try to find the autocorrelation between these two random variables, and it is defined as Rxx. So I will define it as capital R X T1 T2 capital R X. Yeah. So you can denote it as you feel is like you are comfortable with. So I will use capital R XX T1 comma T2. So we will use the same standard notation all throughout the course. So RXX T1 comma T2. So this gives us the autocorrelation function. This gives us the autocorrelation function, right? So this value, right, autocorrelation function, and this function is defined as the expectation the expectation that you get once you take the product between xt1 and xt2. Okay, so the autocorrelation value is the value when you get the expectation between two random variables, and you take the product between two random variables and you take the expectation operation on that. So the value you get will be the autocorrelation value. So this one we can also denote using integration, and that integration will look like this. So xt1. In here I denoted this as capital xt1, but in this one I'm going to denote it as simple xt1, xt2 to denote each and every value of the random variable, and the corresponding PDF function that will be the joint PDF of both these random variables. It's going to be fx xt1 xt2. So I will just denote it as fx1 x2, right? So I will just denote it as fx1 x2. This is a joint PDF function, and this one is a joint PDF function, and we can denote we need to integrate it over x1 and x2 random variables to get the integration over these two random variables. Then this equation or integration will give us the autocorrelation value, right, between the two random variables xt1 and xt2. Apart from that, we also can denote the autocorrelation for a discrete random process. For a discrete random process, we can denote the autocorrelation function using two summations over the discrete values of these two random variables. So we can denote it like this. So for the range of x values, we can get the summations. So the summation will happen over the range of x values that we can get for the two random variables. So for the discrete random case, you are using the summations basically, and you are using the integrations for the density functions which occur with the continuous random variables. So do you have any questions so far? Right, so I will go ahead. So auto covariance function, right? Auto covariance function. So one thing I want to mention with these auto terms, right? Auto covariance, auto correlation, they refer to the same realization, right? To the same sequence. So same sequence is considered, right? So same sequence is considered and two variables in the same sequence is considered, right? So we are considering two variables in the same sequence. We are comparing those two. So two random variables of a same sequence are considered to compute this autocovariance. Autocovariance is denoted using this equation. We will denote the covariance as either COV or CX, let's say, right? So autocovariance we can denote as COV or let's say CX, COVX, and then inside, right, inside the bracket, it should be T1, T2, whatever the time instances you have considered, equals the autocorrelation function between T1, T2 minus the expectation of the expectation at T1, T2, right? So how does this come, right? So, you know that covariance. Now this is covariance, right? So covariance, the definition of the covariance we need to first understand first in order for us to understand this output. So if we consider the covariance value, it's going to be the expectation of a certain random variable at xt1 minus the mu value at that t1, or the mean average of this random variable at t1. Then we are going to multiply it with the uh, the other random variable xt2, which is right, which is mu t2, right? Other variance is denoted using the xt2 minus mu t2. So by taking these products, we can get the covariance between these two random variables. So these are the two random variables, right? The variables are these xt1 and xt2. So these are the random variables, right? xt1 and xt2. So these ones are fixed. These are fixed constant values, mu1, mu t1. So can you try to derive this expression from this equation? Can you try to derive it? Right? I will give you 2 minutes. Try to derive the equation in the first line using the equation in A. Okay. So actually this one we did last week as well. So same computations that we did last time will be done here as well. So starting from this definition here from equation A, we can write expectation, and inside the expectation we can take the multiplication between these two brackets, right? So we have xt1 into xt2 and minus mu t1 into xt2, then minus mu t2 into xt1 plus mu t1 mu t2. So when we so these all should be inside the brackets, and when we take each of these components out, xt1 xt2 we will take separately, and then we will take the expectation of that. So this expectation we have defined earlier as to be equal to the correlation between T1 and T2 variables, right? So this is equal to correlation of T1, T2. From the definition, this X term is Rx T1, T2. So, so we can denote. So I will put double X here, right? So it should be correlation between T1, T2 variables. So earlier we defined using two X values on the bottom. So we will use the same definition here. So basically this will equal to Rx x T1, T2. T1, T2, then minus. Then we have this these values, right? The rest of these processes to be done. In here, once we take the mu T1, which is a constant, right? This is a constant value which we get as the mean value. It is a fixed value. So because of that, it is a constant. Therefore, we take it out. Then we will take the expectation of xt2 minus mu t2. We can take it as a constant, and we take the expectation of xt1, right? So xt1, xt2 are random variables. So they are variables. And then we are left with these mu terms. So mu terms are constants. So they will remain as same even though we apply the expectation operation. So once we take these into consideration, what will appear here is mu t1, in here mu t2 minus mu t2, mu t1 plus mu t1, mu t2, right? So likewise, we can get the final values for this step. So in here we see that these are equal, so we can cancel out the effect of one on the other. Then we are remaining with this expression. So it is the expression that we wanted to achieve, which is in this place. So we try to achieve this expression. So basically, the covariance of the two variables at T1, T2 are given using this function, where the autocorrelation between T1, T2 are subtracted with the product of the means of the T1, T2 variables. So this equation you might need to remember. You might need to use that in your calculations. So maybe you might need to remember this. So it is actually a useful equation, and you can actually use it for some kind of a calculation, and you can derive it on your own as well, starting from the first principles. So because of that, sometimes you don't have to memorize it. You can derive it using the first principles. So if you have any questions, you can let me know. So this is the covariance that we found, right? And we found about the correlation. So if we take specific instances where the time value, the time is equal, or if we consider same, if T1 equals T2, right? Which means that if we consider situation where the time that we are considering is same, that means that the variable xt1 and so we are considering a case where we are comparing the same variable. In that case, the autocorrelation will be equal to x rxx t1 or t comma t1, right? So that one I will define as rxx t1 comma t1. So this means we are actually counting the correlation between the same variable. So that one will be equal to ex t1 into xt1, right? So which is like e xt1 squared, right? Because we are considering the same variable, and we are, by the definition, we are taking the product between the two random variables to find the autocorrelation. So if you are finding the autocorrelation between these two values, these two random variable values, then we get the random variables, then we get the autocorrelation from this equation. So the autocorrelation value will be equal to E, or expectation of xt1 squared. xt1 squared, we will consider, and we will take the expectation of that. And then when we consider, right, when we consider the autocovariance, autocovariance, it will be also the case where we substitute T1 equals T2, right? So before that, now for a general case, the autocorrelation at the same time will be denoted using, for a general case, it will be denoted using T as the time instance, and we will denote the expectation of that operation like this. So we can denote the square term in front. Then we can denote this as the this as the equation that you can use to find the autocorrelation between the same random variable. Then autocorrelation between the same random, autocovariance between the same random variable can be found by taking the same t value for both the signal, for both the random variables, and then you can define the autocorrelation function as t comma t minus mu t into mu t, right? So this autocorrelation function we have defined earlier as ex squared t inside brackets, then mu t squared, right? In here we get in here you get mu squared t, right? So this is equal to actually the variance of the random variable at t equals specific t. So the covariance value will be equal to sigma squared at this point, right? So we know from our definitions that once we take the once we subtract the EX squared with mu squared, we are able to find the variance. So this equation is something we already defined in the last classes to find the variance of a random variable. So in here also the same equation is used. Only difference is that previous, right, compared to the previous case, in here the random variable is the random variable at time t, right? So this random variable at time t is considered as the random variable. So that is the only difference that that we consider in this instance with the random processes. So the final covariance value will also depend on this random variable at time t. So with those statistics, we can define the covariance, right? So those are the important statistics to define the behavior of a random process, right? And so in the next part, we have to learn about the types of random processes. So, right? So types of random processes we have to discuss about. So if we So the types of random processes can be divided into multiple random processes, right? So we will only discuss about specific types of random processes in this module. Although there are multiple other types of random processes available in the statistics and in signal processing and so on. So in this module, I hope to focus on specific types of random processes and focus on their behaviors. So one of the types of random processes is independent and identically distributed random processes. Independent and identically distributed random processes. Identically distributed random processes. So these kind of random processes are known as IID random processes. IID random processes, independent and identically distributed random processes. These are very commonly used random processes. So the definition of these random processes we will learn, right? So before these random processes, we have to define the behavior of independent random processes. So independent random processes we will discuss first. So independent random processes comes first. Then secondly, independent and identically distributed random processes comes second. Thirdly, we will discuss about uncorrelated random processes. Uncorrelated random processes, right? So I don't know whether you can remember in the last class we have discussed about independent random variables, uncorrelated random variables, and thirdly, orthogonal random variables. So we have basically these characteristics to the random variables. So when we consider like one, two or more random variables, we will use these terms to understand the interdependency between the multiple random variables that we are considering, right? So these parameters are used to identify the interdependency between, they are used to find the interdependency between the random variables or the random processes, right? So so when we come back to the types of random processes, there are uncorrelated random processes and there are also orthogonal random processes. Orthogonal random processes, and we also have other types of random processes such as stationary random processes. Then we have ergodic random processes. Ergodic random processes. So those are the types of random processes that we will be focusing more, mainly because of their importance in the signal processing domain. So because we'll be using them multiple times. And so when we discuss about the independent random process, so we will discuss first about the independent random process. So do you have questions so far? When we talk about the independent random processes, independent random processes are almost equal to the independent random variables that we discussed in the last class, right? So independent random processes means that the random variables behavior of, I mean, the behavior of a certain random variable xt1 is it's basically not affecting the behavior of another random variable xt2, right? So this random variable is not affecting the other random variable. So likewise, each of the random variables behave independently, and therefore we are taking that the probability density function of the joint density function, right? The joint probability density function of all the independent random variables is the product of all those random variables taken separately. So when we take the random variables x1, x2 up to some kind of xn random variable that is available, we will take right? We will take up to certain time. I mean, we are going to calculate the random variable values until a certain time instance. So we will take the maximum time instance we are considering is time equals n second, and then we will take the joint PDF function, right? The joint PDF function and its value we can take as the product of that random variables probability density function individually, right? So individually we can take the probability density function of each variable, then we can multiply them over all the random variables we are considering, right? So this is a random variable related to xk and the probability density function of random variable xk. So if we take this xk, we can multiply this with the other random variables that are defined in this sequence. So from k1 to n, you can take the product. So this symbol defines the product operation, right? So this product operation is denoting the multiplication between the PDFs of each of the random variables that are denoted using the xk. So this is the definition of independency or independent random processes. So if the process is an independent random process, then you can take the probability density function as the product of each of the individual probability density functions as the combination. You can take the product of each density function individually. So the finding the joint distribution function is therefore easy if it is independent random process. So next, second random process type we are going to consider is the independent and identically distributed random processes. So independent and identically distributed random processes are processes that we are most of the time using in communications and other kind of signal processing domains. So independent and identically distributed. Dependent and identically distributed random processes we call as IID processes. IID processes, right? Identically distributed processes. So IID processes right? In IID processes, the main function, main feature that we can see is that all the random variables have the same PDF, right? All the random variables, xn, xt1, xt2, xt3, up to xtn, they are all having the same PDF function. All the random variables have the same PDF function, right? All the random variables of the random process, right? Of the random process, which we denote using xt1, xt2, likewise, up to xtn, right? Xtn, let's say there are n number of time indices. So all these random variables will have the same probability density function. Will have the same probability density function. Same probability density function. Probability density function. All these random variables will have the same probability density function. So if that is the case, that random process is known as the independent and identically distributed process. IID process. Right? So same PDF, then we call that IID process. Then so we can actually we can also define the autocorrelation between these between the random variables in IID process. So autocorrelation we denoted using RXX, and if we have two random variables called xt1 and xt2, right? xt1 and xt2. For the IID case, if the expectation of the xt1 is if the expectation of the random variable xt1 is mu, what is the autocorrelation value? What is the autocorrelation value that you can obtain if it is if this process is a identically an independent random process, right? So we are going to consider a scenario where the xt1 and xt2 are identically independent and identically distributed. So if that is the case, can you tell me what is the value of the autocorrelation? Can you tell me the value of the autocorrelation? right? So the value of the autocorrelation value you find by the expectation of the random variable and the expectation of the product between the two random variables. So so since these are independent, we can say that the expectation operation can be done individually on both these random variables separately. So if we know the value of so we can do them separately for xt1 and xt2. So in here the value of t1 will be different, right? T1 T2 will be different. However, if it is IID process, you know that ext1 and ext2 will be same, right? ext2 will be same. So if we know the value of ext1, which is mu in this case, we can say that both these values are mu. So therefore, the final output for the correlation will be mu into mu, which means mu squared. So finally, you can find the value of autocorrelation for that specific random process with the mean for one random process mu. So you can find the autocorrelation function by saying that the expectation for other random variable is also going to be the same, because the probability density function is same for all the other random variables as well. So which means that the mu value is also going to be same for the other random variables, like for other random variables as well, like xt1, xt2, xt3, like that. So for all the xt1s and xt2, xt3, xt3, so for all the random variables, the PDF function is right. If the PDF function is same, then we have to consider that the expectation operation on these random variables is also going to be the same, and therefore it's going to be that average value is going to be same. So the final value for the autocorrelation will be mu squared. So we will discuss about those mu values and how we right. So we can discuss about these scenarios using another example in the maybe in the next class. So before going for before going further, I will also mention that we have to discuss about the uncorrelated random processes, orthogonal random processes, stationary random processes, and ergodic random processes next. So when we take the uncorrelated random process, so these uncorrelated random processes are also similar to the uncorrelated random variables. So uncorrelated random variables are something that we discussed in the last class. So the definition was that the expectation of a random variable which is uncorrelated should be that the expectation of the product between the two random variables, xt1 let's say and xt2, should be equal to the product individual products of expectations. So it's going to be expectation of t1 right, expectation of xt1 and expectation of xt2. We take those products and then we can find the rest of the we can do the rest of the calculation. So this is the rule for uncorrelated random processes, right? So just so we learned this in the last class as well. The only difference is in here we will be having the t as the parameter that defines a random variable. So this part has been added when we can compare with the last time's lecture. So in the last time's lecture, we considered two random variables, x and y, and then we consider that if they are uncorrelated, then the product between x and y, the expectation of the product between x and y should equal to the expectation of x into expectation of y. So in this case, when we have the random variables, then the expectation of the product between these two random processes, xt1 and xt2, should equal the expectation of xt1 and xt2 processes. So this is the uncorrelated, I mean the condition for showing that a certain random process is uncorrelated. So so if there are two random processes that are independent, they will definitely be uncorrelated. So if there are two random processes which are independent, they will be uncorrelated, right? Independent random processes will be uncorrelated. Will be uncorrelated. However, if there are uncorrelated random processes, we cannot ensure that it will be independent all the time. We cannot ensure this, but all the time, independent random variables will be uncorrelated. So this happens all the time. So with that, actually, I would like to end today's discussion. So if you have any questions, you can ask. Right? So I will stop the recording. If you have any questions regarding